Okay, in this video I'm going to show how to use the results that we have from the previous video and use them to solve a problem. So in this case, problem 12.29, a ball A is thrown vertically upward. Okay, that is telling us that it's in free fall, because once you let go of it, nothing's touching it. So you know that the acceleration is downward with 9.81 meters per second. Thrown vertically upward from the top of a 33-meter high building with an initial velocity of 5. Okay, so since he's saying he's throwing it up, I'm going to call it up is positive. I'm going to say that that's a initial velocity of 5. At the same instant, another ball B is thrown upward from the ground with an initial velocity of 28. Determine the height from the ground at which they pass. Okay. To do this problem, the first thing that we want to do is make sure that we can do this using Chapter 12 things and not Chapter 13. So what we do is we count the degrees of freedom. In this particular case, ball A has 1 freedom because it can move vertically. Ball B has 1 freedom because it can move vertically. So this is 2 degrees of freedom in this problem. What that will tell us is we have to have 2 accelerations, or 2 velocities, or 2 something. And so the question is, do you have 2 accelerations? Yes, you know that both balls have an acceleration of g downward. So because it's 2 degrees of freedom and I know 2 accelerations, I can solve this problem. That's how I know I can do it. Okay. Because the acceleration of both balls is a constant, I can use the handy formulas that you saw in the results video. So that's what I'm going to use. Now, there are 3 equations. If you look at your notes, there are 3 equations. Now, this particular problem is telling me, I know, well, I mean, this free fall. So I know the accelerations, and what it's asking me for is determine the height. That's a position. So they're asking me to find a position when I know accelerations. So that means that you're going to integrate these things, right? That's how I got those equations. I integrated acceleration. So I'm using the handy formulas. Now, they are telling me or asking me to find position, and they are giving me acceleration. So I'm going to look at the 3 equations, and I'm going to try to determine which of the formulas I would like to use. In this particular case, the first formula relates position with velocity and acceleration and time. The second equation relates velocity with acceleration and time. And the last one does velocities with positions. So the only 2 that I really should think about is either the first one or the last one, because they're the only 2 that have position in them. Okay. What I'm going to do is stop this video. I'm going to pull up some handwritten notes and go from there. But you might want to just remember these numbers. You'll see them in the paper. Okay, you'll see this file in the notes as well that are posted. So we're doing this problem 12.29. We know it's 2 degrees of freedom. We know 2 A's, so we are able to solve it. So because g is constant, we're going to use the handy formulas that we had before, which you'll see in a minute. Okay, when you're setting this up and you need to be able to define position or anything else, first thing to do is pick an origin. You can pick any point as long as it's fixed. Your answers will be the same regardless of which origin you pick. So even if you pick an origin different from someone else, it'll work out. In this particular case, I'm going to pick the origin right here at the corner, because it looks convenient, it's easy to measure things, etc. Okay, if you want, you could define it up here at the corner, whatever you want to do. Okay, I'm going to choose mine down there. So that's 0. I'm also going to choose up to be positive, so that's a positive direction. So make sure that you do that. Okay, so because it's 2 degrees of freedom, this is new information. Because it's 2 degrees of freedom, I'm going to expect to have to write 2 dynamic equations. Okay. In general, you're going to write, if it's a point, you're going to write 3 equations. several of those will be constraints. So I'm going to write two equations that are not constraint equations because it's 2 degrees of freedom. Okay. Because they want position, I want one of the handy formulas that has position in it. And there's only the first one and the third one, if you look back on the results, that have position. If you look at equation number 3, the last one, it has position, but it also has velocity. So I don't know anything about this velocity. That would be a good equation if, for example, they said, how fast are they going when they happen to be at 50 feet off the ground or something. That would be great because they want to know velocity, and they're telling me position. But if you have both of these unknown, I don't know where they intersect, and I don't know how fast they're going when they're there. Those are two things. It's too many unknowns. But if you look at the first equation, it has position, right, just like the other one. It has time. So what I'm going to do is I'm going to say, well, I'm going to find the time for A to do something, and also it'll be the same time for B. So anyway, those are very typical. Okay. When they pass, right, which is what they're asking me for, when they pass, the position of A is going to be the same thing as the position of B, because that means that they're at the same place. They're passing each other. So that's the key to solving this problem, is that they're telling me that the position of A equals the position of B. Therefore, but when they pass, I don't know anything about their velocities. So what I'm thinking is that number 1 is probably the best thing to use. Okay, so here we go. Here's the number 1 equation. Position of A is equal to the initial, original, whatever you want to call it, position of A plus the original, initial, whatever, velocity of A times time, minus, because the accelerations are downward, 1/2. The A happens to be the number g, t squared. This equation over here is the same equation, but it's applied to B. 2 degrees of freedom, 2 equations, 1, 2, right? Okay, so now let's just put in the initial values. Okay, what's the original position of A? Well, it's at the top of the building when everything starts. So it is 33 above in the positive direction, 33, so it's a positive 33. That's its initial position. How fast is it going originally? Well, according to mine, now the numbers are randomized, so yours may be different. But my problem said that he was being thrown up at a speed of 5. And so that's why I put in a positive 5. He's being thrown up at 5 times t. The t0 in this case is equal to 0 because at the very beginning, that's when both balls are thrown. And then you have the 1/2 A happens, or is the value of g. Okay, plug in the initial things for B. The position of B is equal to, here, B starts at the origin, so he's down on the ground, so that's 0. He's thrown at 28 up, and then the 1/2 g, just like the other one. Okay. When they cross, these guys are equal. So this stuff here has got to equal this stuff here. Right? That's when they cross. And so you say, okay, this guy is equal to this guy. Right? So I just copied them down. And then you solve for t. Right? Well, if you notice there's a minus 1/2 gt squared and a minus 1/2 gt squared, those are gone. So this is not too bad. It's 33 plus 5t. And over here you have 28t. So solve for it. Boom, boom, boom. There's your time. Now that you have your time, what you do is you can put the time into the B. So just take this t and shove it in, well, I guess right in here, right? There and there. Or you can take the same t and you can shove it into this one. Boom, right there, right there. Whichever one you think is easier. I think it's easier to use this one. It doesn't have as many terms. So you just pull this down and 28 times t minus 1/2 g times t squared. Bang, pull out your calculator and you get your number right there. So that's how you do that problem.